We've made it to the very last topic of the semester. This will be our final video with new material, new content in it, right? That last topic is what is known as LeChatelier's Principle, which is something that lets us figure out the direction of response of an equilibrium system if we do something to disrupt it. So let's go ahead and get started into that. So stated in words, LeChatelier's principle is kind of awkward, like a lot of things. I feel like I'm always saying it's hard to explain by just putting words in front of you. But LeChatelier's principle says if we impose a change on a system at equilibrium, the system basically will fight back. It will react in the direction that reduces the amount of that change. Okay. A change in this case could apply to any number of things. Most often it might apply to just adding or removing some material, something from the reaction, okay? If I am forming a product and maybe I just remove the product gradually as the reaction goes along, that will keep it from getting it or staying at equilibrium, okay? Some reactions involving gases, we can often change the composition by changing the pressure on the system, okay? And finally, the most dramatic change if we change the temperature, because if we change the temperature, not only does that knocks the system out of equilibrium because it would change the value of the equilibrium constant, right? We always say the equilibrium constant is equal to this at a particular temperature, and that's because that equilibrium constant is very much a function of temperature, okay? The best way to illustrate this is just to look at a reaction and see what would happen if we were to remove some of the materials, say, and that's what we're going to do here. So here we have a system at equilibrium. What our reaction is reacting CO2 and carbon tetrafluoride, and it's making COF2, what would be carbonyl fluoride. That product over there is actually somewhat useful in the semiconductor business because it's one of a number of compounds that can be used to etch silicon. And so it says we have a system in equilibrium. It's at 1,000 degrees C, so it's pretty hot. It's in a 10-liter container, and it has those numbers of moles of the three substances, okay? We're going to see what will happen if we were to remove all of the product, the COF2, okay? And then what would happen to the amount of CF4, what would be the final amounts of everything when the system gets back to equilibrium is what we're eventually going to calculate, okay? So there's actually a bit to do here. What do we know? We know initially our system is at equilibrium, all right? So let's start there. Those numbers there, the 0.99, 0.714, and so on, those are numbers of moles, and it's in a 10-liter container. And so that means we're going to divide each one of those numbers of moles by 10 to get the molarities, right? Because our equilibrium calculations are always about molarities. So here's my reaction, and I'm going to do something a little bit different in my chart here. I'm going to say this is the initial equilibrium because it starts off at equilibrium, right? So the first time I come to the system, EQ, not EX, and at that point, my molarities are 0.099, 0.0714, and 0.057, okay? And those, again, those are at equilibrium. That means I can use those numbers to find the value of the equilibrium constant because I don't have that yet. I'm going to need that to do the calculation at the end. So I'm just going to say now my KEQ, my equilibrium constant for this, what in the textbook is often referred to, or in the OWL things, as Kc, where C is for concentration, because you can also write these things in terms of pressures, but we're not doing that for our purposes here. COF2, that's squared. That's because I've got 2 moles of that on the product side. I've got CO2 and CF4 from the reactant side, right? So that's my expression. I put in the numbers. And if I solve that, I have a note beside me that says I get 0.46 for my equilibrium constant value for this reaction, okay? So now I know the equilibrium constant, and I'm going to go about doing the latter part of the problem from here, okay? So I'm going to start again because I didn't put this up here, I guess. So here's my initial equilibrium. And that's the one we had before, right? So that's 0.099, 0.0714, 0.057, then we're going to remove all of the COF2 is what it says. So we're going to have what I'm going to call the new initial or the new start. I'll use start since I used initial above, right? But that says at the instant that I remove the COF2, these haven't changed. This goes to 0, right? Because that's what it said. It said somehow we take out all the COF2. Right. In a lot of reactions, people actually do something sort of like that by, if the product, say, has a lower boiling point temperature than the reactants, you could have some surface that was cooled enough that the product would condense onto it, and then you could remove it that way. That's one way to accomplish such a separation, right? So now I have a system that's not at equilibrium, right? I can look at that and I can see what my direction of change is, right? Because now I've zeroed out the right-hand side. So my changes from there to go back to equilibrium, right? Once I've removed the COF2, my system's not at equilibrium anymore because obviously it has no product, right? So my Q for this system right now would be 0. That means it has to go this way it has to go from left to right. So I'm going to have minus x, and plus 2x for my changes because I make 2 moles of COF2 when I lose 1 mole of each of the others, right? So my new equilibrium, let's say, is now 0.099 minus x, 0.0714 minus x, and this one is just 2x, right? So now I have to get myself an equation that I can use to solve for x, right? And that equation comes from the equilibrium constant, right? So I have that k, the equilibrium constant, is always got to be equal to my products over reactants expression. Right, which is now equal to, well, I know it's equal to 0.46 because that's what we calculated a moment ago. And now I know that's also equal to 2x. That's squared because that's the concentration from the top. Down here, I have 0.099 minus x. And I have 0.0714 minus x. All right, when we get to there, we have, again, accomplished all the chemistry part of things, okay? Because now we've just got an algebraic equation for x, and once we get x, we know the concentrations, right? Alas, looking at that one, there is no way out of that equation other than solving it, multiplying it out and doing the quadratic formula to solve it, okay? I'm going to go ahead and write in at least parts of this solution here, I think, in the interest of completeness, and then we'll come back and pick up the table stuff there, okay? So if I multiply that thing out and rearrange it a little bit, I get 4x squared equals 0.46 times x squared minus 0.1704x, it says in there, plus 0.00707. Which a little bit more jiggling, and that gets me to 0.07. All of that equals 0. I put that into the quadratic formula, and I'm not going to write out all the quadratic formula solving steps, but I will tell you that when I did that, I got x equal to 0.0212, and the second root is minus 0.0433. right, of those two roots. If I look back here, 2x is the concentration of the COF2, right? That tells me x has got to be positive, right? The boundaries on x here are that it has to be positive, and it has to be smaller than 0.0714, I guess, because if it broke either one of those conditions, then it would cause at least one of the concentrations to become negative, and we can't have a negative concentration, right? So that means I drop this root, I keep this one, right? And then that gives me my final concentrations, which said the CO2, that one was equal to 0.099 minus X, and that's 0.0778. The CF4 is equal to 0.0714 minus X, which gets me 0.0502. And lastly, the COF2, that one is just 2x, which will be equal to 0.0424. Whenever you solve one of these, there's actually a built-in check if you're interested in doing that sort of thing, which is I could take those things I calculated for the equilibrium concentrations, and if I pop them back here into this expression, I should find that I get essentially get the equilibrium constant back. Okay, it might be off a smidge from some rounding. There's obviously some numerical wiggle room in doing this because we've got the square roots flying around and lots of things in there that can give us some degree of uncertainty, but we should get something that is at least essentially equal to the equilibrium constant. Otherwise, we've done something wrong. Okay, so that's sort of how LeChatelier's principle works, right? In this case, what's the perturbation, the disruption of my equilibrium is that I took out the COF2 from the right-hand side. So what does the system do? It puts some stuff back on the right-hand side. Right, it doesn't end up with as much CO there, right? I ended up with a concentration of 0.0424 rather than the 0.057 that I had in the first equilibrium. I can't get back to as much because if I made that amount of COF2, I wouldn't have the same amounts of the reactants left, the CO2 and the CF4, right? And so it finds its way to the new equilibrium. If I had put more COF2 in, it would have said, there's too much of that now. It would have gotten rid of some of it and moved it to the left-hand side. Okay, so that's how we handle LeChatelier's principle in the case that we're changing the amounts of stuff. All right. One last idea for us, and that's how this works with temperature changes. All right. The easiest way to figure out which way a reaction will shift if you raise or lower the temperature is to take some thermodynamic ideas and think of heat as being either a reactant or a product. Right? That's a little bit weird, but it kind of makes sense, right? In an exothermic reaction, we make the product substances and we also liberate some heat, right? So it's a little bit like heat is produced, heat is given off, right? And so in that case, heat is a product. If I raise the temperature, that's like adding heat to my system, right? So if I raise the temperature, putting heat into the system is like putting something in on the right-hand side. So that would move the equilibrium to the left. So if my reaction is exothermic and I raise the temperature, I'll actually get less of the product and more of the reactants when I'm at equilibrium, right? If it's endothermic, the opposite will happen, because if it's endothermic, then I think of heat as being like a reactant, right? Because heat's flowing into the system. In order for the reaction to go and form the products, I have to have that heat input. Right? And so in that case, if I raise the temperature, the equilibrium will shift to the right and I would make more products, okay? It's more complicated to calculate the extent of these changes because if we change the temperature, the actual value of the equilibrium constant changes, okay? There's a reasonably straightforward way to figure that out. At this point in the semester, pretty much every year I decide that there's no point in tossing another equation on us, and so I will once again refrain from doing that, but we should have the qualitative picture of which direction things would go. These have some significant implications, right? There's a trade-off in doing this, right? If you're doing an exothermic reaction and if your goal is to make the product, right? Well, this says if you raise the temperature, that means at equilibrium, you'd get less product, right? That's not a good thing, right? On the other hand, if you raise the temperature, the reaction will go faster, and that often is a good thing. So in lots of cases, there's a compromise between that. Do we want to have it produce more product at equilibrium, or do we want to have it do something faster? Usually the solution to that is that in the chemical business, most reactions are not allowed to actually get to equilibrium. People engineer various schemes to just keep removing the product as time goes along so that you never build up product, because that way you can keep your reaction wanting to go from left to right, assuming that the stuff on the right is what we're trying to make. That's our literal business product that we want to take out and sell. Then if I don't let that build up, then I don't have to worry about the equilibrium constant part. And then heating the system up makes the reaction go faster, and that's usually a net win if your goal is to get the product and take it out in the world and sell it. All right, that wraps up all of the material that I've got for you for the semester. Our remaining couple of class periods we will spend in a little bit of retrospective or review of the second half of the semester.